Hi everyone, so now we've learned about how to find the volumes and surface areas of several different shapes. We're going to talk about scale factor. And scale factor, the formal definition is the ratio between two corresponding sides of similar figures. It says of similar sides or corresponding sides, but basically with scale factor, what it's saying is that if I had a small version of something and I wanted to blow it up bigger, I can do that by multiplying it by a scale factor. So if I wanted to double the size, I would just double each side of the figure. Or if I wanted to take a bigger thing and make it smaller, like a scale model, then I would divide it by the same thing or multiply it by the same fraction, all of the sides, so that they would go down in the same way. So even though this definition says that it's the ratio between two corresponding sides, it can also be the ratio between two surface areas or the ratio between two volumes. And that's kind of what we're going to do in these examples today. The other thing that I wanted to talk about before we get started is that a ratio is just a fancy name for fraction. And so all of these will just end up being fractions or something similar to fractions, but we'll start going through this. So for the first two examples, each pair of figures is similar, and we want to find the scale factor. So when it tells us that each pair of figures is similar, that just tells me that they should look the same, they just might be bigger or smaller than the other. And so the good news, or this is easy because what they're doing is they're giving us for this first example, they're giving us the surface areas of both of these things. Because they're giving us the surface areas of both of these shapes, we can just compare the surface areas. Like I said, the scale factor is comparing two of the same thing. Because these are both surface areas, we can just compare them both. If it was like a surface area and a side length, we would have a harder time. Or if it was a surface area and a volume, we couldn't do that. But because they're both surface areas, we can just compare them side by side. So the question wants us to compare the left shape to the right shape. And so the way that I like to write it out is that we're going to compare surface area of the left shape on top over surface area of the right shape on bottom. And if I do that, I would end up with 64 meters squared, because that's the surface area of the left shape, over 36 meters squared, because that's the surface area of the right shape. So what we're going to do now is just simplify that. And so the first thing I notice is that both of these have a meter squared. I have a meter squared on top and a meter squared on bottom. Because that happens on top and on bottom, I can cancel them out. So now I'm just left with 64 over 36. Scale factor does not have a unit, so there's not like a meters or a meter squared on this. It'll just be a fraction, or it'll just be a number. And now we can simplify the 64 and the 36. These are both divisible by 4, so I'm going to just divide each chunk by 4. When I divide 64 by 4, I get 16. When I divide 36 by 4, I get 9. And this is as simple as it'll go. So my scale factor is 16 over 9, which basically means that in order to get from the small shape to the big shape, I needed to multiply by 16 over 9. Okay, so let's do the same thing for the second example, and I didn't write it down. So let me write it down. So the second example is two cones. And the first cone has a volume of 64 pi inches cubed. And the second cone has a volume of 8 pi inches cubed. So again, these are volumes, but because they're both volumes, we can compare them. It's like comparing apples to apples instead of apples to oranges. And so I'm going to say the volume of the left cone over the volume of the right cone. Because remember, we're doing a ratio, which just is a fancy name for fraction. I know that the volume of the left cone is 64 pi inches cubed, and the volume of the right cone is 8 pi inches cubed. And once again, we're going to just cancel out stuff that happens on top and on bottom. So the units of inches cubed happen on top, on bottom. So those can be canceled out, which leaves me with 64 pi over 8 pi. And then I have a pi on top and a pi on bottom, so those will cancel out, which just leaves me with 64 over 8. Now, both of those are divisible by 8, or I can actually just do 64 divided by 8. 64 divided by 8 is 8. My scale factor is 8. It doesn't necessarily need to be a fraction. My fraction in this case would be 8 over 1, but that doesn't matter. All it's saying is that I took the smaller shape and I multiplied it, or I blew it up by 8 times to get the bigger shape. Okay, so now let me draw this third example. In the third example, we have two pentagonal prisms, and it's going to be a little bit harder for me to draw pentagonal prisms. So I'm just going to draw the pentagons. And we're going to say that the height of these pentagons is, we've got a 3 yards for a height, and then the side length is 10 yards. And then this next one, we have 27 yards and 90 yards. Basically, instead of giving you a surface area or a volume, they're giving you side lengths. Again, this is totally fine because you can still compare the side lengths to side lengths. So in this example, the first thing we need to do is find the scale factor, get the same way as what we did on example 1 and 2. And then once we find the scale factor, we're going to find the ratio of the surface areas and the ratio of the volumes. So first, let's find the scale factor. And I'm going to do it the same way that we were doing example 1 and 2. We're going to do the side length of the left side over the side length of the right side, which you can decide which side length you choose. You wouldn't choose, like you would either choose to use the 3 yards and the 27 yards, or you would choose to use the 10 yards and the 90 yards. You wouldn't choose to use like 3 and 90 or 10 and 27. You have to compare the same thing. Like we were comparing surface areas to surface areas and volumes to volumes. So we have to compare side length to side length or height to height. I'm going to use the 10 and the 90 because those look like easier numbers. But the 10 is from the left, so we've got 10 yards on top and 90 yards on bottom, which means that, again, we can simplify by canceling out those yards. And then we get 10 over 90. Those are both divisible by 10. I can divide both of them by 10 and get 1/9. What that tells me is that to get from the shape on the right to the shape on the left, I have to multiply by 1/9 or divide by 9. So this 1/9 is my scale factor. Okay, now that I know the scale factor, I want to find the ratio of the surface areas and volumes. So this is where it gets a little bit trickier, but it's still pretty easy. I'm going to have this ratio of 1/9, and I want to find the surface areas and the volumes. Now, based on what we were doing in those previous videos for this lesson, you could potentially find the volume of each of these and find the surface area of each of these, but I'm going to show you an easier way if you know the scale factor. So what we're going to do is, basically, we want to find the ratio of the volumes and ratios of the surface areas. We don't actually care about the actual surface areas or the actual volumes. So if I know that the ratio or the surface areas are 1/9, or I'm sorry, not the surface areas, but the ratio of the side lengths are 1/9, then the ratio of the surface areas, what I'm going to do is just take that 1/9 and square it. The reason why I'm squaring it is because I'm going from side length to surface area, and surface area units are always squared. So I have to square the side length scale factor to get the surface area scale factor. When I square that, what happens is the squared goes to the top and the bottom, so it's like 1 squared over 9 squared, which gives me 1 over 81, and that's my ratio of the surface areas. So I'm going to say that that's for the surface areas. Okay, and then we're going to do something really similar to find the volumes. volume units are cubed, so I'm going to take my surface area, and instead of squaring it, now I'm going to take my side length ratio, and instead of squaring it, I'm going to cube it to get it to volumes, which would give me 1 cubed over 9 cubed. And we know that 1 cubed is 1, and then 9 cubed is 729. And so the ratio of my volumes is 1 to 729, which means that I would have to get from one volume to the next volume, I'd have to divide by 729 or multiply by 1 over 729 to get the different volumes. Okay, so that's how we find the ratios of surface area and volumes, given that we already had a scale factor. Now, in this last example, we're going to take it one step further. Let me just write out what it has. So we know that the scale factor for some shape is 2 to 3. Now, that's a fancy way of writing just a fraction 2 over 3. So we can write it this or that way or that way. We also know that one of the surface areas is 192 meters squared, and then one of the volumes is 640 meters squared. And the goal here is to figure out the surface area of the surface area and the volume of the other shape. So we're going to do it really kind of similar to what we just did in that last example. If you remember, we took the scale factor and we squared it for the surface area, and then we cubed it for the volume. So I'm going to take that scale factor, which is 2/3, and I'm going to square it. And what I'm going to do is compare that to the surface area that I already have. I know that one of my shapes already has a surface area of 192. My smaller shape has the surface area of 192 meters squared. I don't know what my bigger shape is, so I'm just going to put an X down here. And now, this is comparing, so this is like my scale factor is over on the left, scale factor, and then on my right, I have surface area. So that, when I square the scale factor, that gives me the surface area. And so this, again, like, it's kind of like comparing apples to oranges now, but I can do that as long as I square the side length or square the surface area, oh my goodness, I'm sorry, lots of S words. As long as I can square the scale factor, that way I can compare it to the surface area. So let me simplify this a little bit. When I square it, I would have 2 squared over 3 squared is equal to 192. And I'm not going to put the meter squared on here until I get my answer for X. I know my X will be in meters squared because it'll be a surface area, but we can just kind of keep the units on hold until we get to that point. And then we're going to simplify that even more. 2 squared is 4, 3 squared is 9, and then we're going to compare that to the 192 over X. And now we have two fractions that are set equal to each other. So when we have two fractions that are set equal to each other, we can cross multiply to solve, which means we're going to do 4 times X, which gives me 4X. And then we're going to do 9 times 192 on the other side. And so we should have 4X is equal to 9 times 192, gives me 1728. And then we can divide each side by 4 to get what X is. So X would be equal to 432. And again, we know this is a surface area because that's what we were doing. We're trying to find the surface area of the other side. So it has to be in meters squared. The reason why it's in meters is because my other shape was in meters, and it's squared because it's a surface area. Okay, so we're going to do something super similar to find the volume. We're going to start with our scale factor, which is that 2/3, but because we're comparing that scale factor to a volume, we have to cube the scale factor this time. And now our volume, we know that the smaller shape has a volume of 640 meters. That should be cubed right there. Meters cubed. We don't know what the other one is, so we're just going to put an X on the bottom to make it a bigger, to find that bigger volume. Okay. So now let's simplify this. The first thing I'm going to do is cube both the top and the bottom of my scale factor. So I've got 2 cubed over 3 cubed is equal to 640. I'm going to drop the unit over X. We're going to actually cube those numbers. So 2 cubed is 8. 3 cubed is 27 is equal to 640 over X. two fractions that are set equal to each other, so we can cross multiply, which would give us 8 times x, which is 8x, and then 27 times 640. And so now when we simplify that, we would get 8x is equal to 27 times 640 gives me 17,280. Then we just divide everything by 8 to get x by itself. And we would end up with x is equal to 2,160. And this is a volume, and we know it's in meters, so my answer has to be meters cubed. And this is the volume of the bigger shape, or the second shape, based on the scale factor we were given. So this last example was a little bit harder just because it took a couple of extra steps, but just remember that in scale factor, it's a comparison of shape to shape. When you find scale factor, you have to compare surface area to surface area, volume to volume, or side length to side length. And then if you want to use a scale factor to find a surface area or a volume, you have to square it for surface area and cube it for volume. And that's how we use scale factor.